Hello, my name is Nicolás Cardoso. I'm from Universidad de los Andes, and today I'm going to talk about some ongoing work we have been developing with my colleague Ivana Usparik at Trinity College Dublin around the topic of generating adaptations for context-oriented systems. So before going into the details of our presentation, let us take me back to the invitation. Hello, my name is Nicolás Cardoso from Universidad de los Andes, and today I'm going to present the ongoing work we have been doing with my colleague Ivana Lusparik from Trinity College Dublin around the topic of generating adaptations for context-oriented systems. Before I go into the details of the presentation, let me take us to the very beginning of context-oriented programming, taking into account the definition of context-oriented programming. So if you go through the literature of context-oriented programming, you will see that there is a common theme across all of the different papers out there presented at the context-oriented programming venue and some other venues around. And the common theme on the definition of what context-oriented programming is a technique to enable dynamic adaptation of the system's behavior to the changing environment. So to represent this, I'm going to use the prototypical example of the smartphone, in which the smartphone behaves differently to incoming calls depending on the particular situation. So the base behavior of the smartphone here at the top of the slide is to just ring whenever it receives an incoming call. However, this behavior can be adapted, or we can vary the behavior depending on the particular situation in which the phone is. So for example, if you're in a hospital where the environment requires the phone to be silent, then the behavior of the system should vary from ringing to just vibrating, so that whenever you receive an incoming call, automatically the phone is going to vibrate instead of ringing. You can change between these behaviors dynamically whenever you enter one of these situations or not. To develop this, we use context-oriented programming languages. And in this case, I'm going to use the context-based programming language, which is an COP extension to JavaScript, but similar behavior can be found in your favorite COP language to the one I'm going to describe here. So the idea here is that if you're defining this smartphone, the base behavior of the system will be defined in a module here in the top square in the slide, just describing the behavior of the system. So whenever you receive an incoming call, the phone is going to ring. For each of these particular situations in which you want to vary the behavior, you can define a specialized behavior or a partial method based on a context. And this is defined in an independent module here represented in the bottom square on the slide. So here we'll have the definition of this context, which is representing the situation in which the environment situation in which the phone is, and the partial behavior or the behavior variation defining what's the expected behavior of the phone in that particular situation. So in this case, if you're in a silent context, the expected behavior of the phone is to vibrate on incoming calls. And these two definitions are independent models, and we can take this further to have independent models for all of the definitions in each of the parts, defining the context and the behavior variation. So defining the overall adaptation. So the context can be defined in a model, and the partial behavior can be defined in an independent model as the association between the context, the base behavior, and the partial behavior. And we can do this for many different situations. So if in our case of the model phone, we define different behavior here in the rightmost column on the table, we have different behavior definitions for what should the phone do whenever it receives an incoming call for different situations, which are the 4 columns to the left. So in these situations, we have, for example, what happens if you're in an off-hook situation. So whenever you're talking, if you're in a silent environment, if you're in a meeting, or if you have activated the forwarding feature function in your phone. And for each of these situations, we see what's the expected behavior of the phone, and we can start mixing and matching all of these features And the language will dynamically take care of presenting the expected behavior for each of these situations or the combination of these situations. So independently, if you're in an off-hook situation, or for example, if you're in a silent meeting with the forwarding feature activated in your phone. And all of these are defined just like in the previous slide. So each of these situations and each of these behavior can be defined in an independent model. So context-oriented programming is great for modularity, and it does that job really well. So we covered that part of the definition of context-oriented programming that we saw from the literature. What about the dynamicity part? So when you think about the definition of this base behavior and its adaptations, then what is happening is that those adaptations are an abstraction of the observations of the real world and abstracting the situation to be represented as a context and the behavior that you expect the system to have in that particular situation. And you can do this for as many situations as you want. So you can have this for a silent context or a meeting context with the specialized behavior for each of these situations, and you can define as many of these. However, there is a problem with these definitions, and the problem is that all of these definitions have to be given beforehand by the programmer. And it's the programmer's responsibility to observe what the context the system is going to execute in, so in which environment is the system going to execute, and the specific behavior or the variation of the base behavior that you want to see in each of those situations. So all of these definitions are fixed before the system is actually execution. And the conclusion of this is that that is not very dynamic, and you're not actually adapting the behavior of the system to the context, but you're actually just dynamically changing the behavior to some predefined behavior that you have there. So if we go back to the definition of context-oriented programming that we saw before, this kind of like contrast with that definition. So definitely something went wrong at some point in the behavior of context-oriented programming and in the goals that we had for context-oriented programming. And the reason for this is that when developers are designing their system, they only have a partial view on the actual world. And there are a lot of unknowns in the environment in which the system is going to execute, especially if your system has users interacting with it. It is unknown how the users are actually going to interact with the system. It is unknown all of those situations that the system can be in and the specialized behavior that you want to see in these situations. So to contrast this problem and to actually make these systems adapt dynamically to the environment, we introduce we introduce Autocorp, which is a new way of defining adaptations for a system based on the actual interaction of the system with the environment. So dynamically, you start introducing adaptations to the system that don't necessarily have to be defined beforehand. So to talk about how Autocorp works, I'm first going to talk about the intuition behind Autocorp and the main ideas of Autocorp to generate adaptations, and then some of the details into how do we actually make this happen. And Autocorp doesn't work for all the different for any kind of system, and we have some restrictions on the systems that Autocorp is going to work on. So the first restriction is that our system has to have a defined goal. And going further from that, we not only need a defined goal, but we need a way to measure how the system is progressing towards that goal. So as we take actions or execute methods, if you will, while the system is running, then we need to see that we're actually moving towards that specific goal that we have. And the other restrictions that we have is that we need a finite set of states and a finite set of actions for the system. All of these restrictions seem kind of random at first, but I'm going to explain why we need them to develop Autocorp as we go along into the intuition of our system. So To explain how Autocorp works, I'm going to use an example of a warehouse robot that is delivering products from their place in the warehouse to a delivery spot, which is the green square here at the bottom of the grid. You can think of this robot as working in one of those online warehouses. Whenever you purchase a product, then the robot is in charge of going and fetching the product and taking to the delivery area, right? So the idea here is that we need to define, we need to know the environment in which the robot is interacting with. So here we have a set of states that we're going to keep simple for the sake of the presentation. So we're going to keep our warehouse being a 5x5 grid, and we need to have a definition of all the different actions that the robot can execute. So here is moving north, south, east, west, picking up a product and dropping off the product, right? And this is the reason why we need a finite set of states and a finite set of actions, because we need to represent all of these combinations of in which state the robot is and which action is the robot executing to be able to generate an adaptation from those interactions. So the first thing that we need to do is to actually be able to monitor what is happening in the environment with our system, how is the system interacting with the environment, to be able to extract information from that. And the set of states and the set of actions can be as large as you want or as little as you want. It can change dynamically, but what is needed is that you need a way to be able to see that state. So if you expand your state, then you need to be able to take into account that expansion, and the same goes for actions. So to monitor the context, we have these definitions, and we actually go through the execution trace of the system. So whenever the system is in a state and executing a particular action or a particular method, we log this execution as part of the execution trace. And this is an example of the actual execution trace of the robot working. And as you can see, we are encoding all the different states that are relevant for the robot. So the position in the warehouse, or whether it has a product or not, and the action that the robot is executing in that particular state, right? Then we have some information that I'm going to discuss about later, but we can think about this execution trace as growing as much as you want. So whether you use finer grained states or you have more variables to monitor in the state, then the log of the execution trace is just going to grow. Having this log is not very useful on its own, because, well, what can we do about this log? We have just states and actions that are executing in this log, but then how do we actually extract adaptations from that? And the intuition here is that we are interested in action sequences that are executing often in this execution trace. And here I've highlighted some actions that are repeated for a particular state. So the actions here involved in the execution trace just represent actions that took place often during the execution and have the same sequence of actions. And we are interested in these particular actions because that is the expected behavior of the system. So that should be the appropriate behavior if it's the behavior that we are using, that we are seeing more happen more often than not, right? So taking this into account, we can extract that behavior as part of our adaptation. This means that whenever we encounter a particular state, so in this case, the state 0, 0, true, then we are going to extract that as the robot being in a particular special situation in which we are going to execute a set of actions, right? So we can extract that particular state and define it as a context in which the robot is going to execute some specialized behavior than its normal behavior of just executing one of the 6 actions that are available for the robot. And the behavior that we're going to, so the behavior that variation that we're going to define is extracted from that sequence of actions that take place, often in the execution. So how do we actually make all this magic work? The idea of Autocorp is that we're relying on a technique of reinforcement learning called reinforcement learning options that is modeled in this model to the left, and actually broadly works in these 3 steps of the algorithm execution. So we extract action sequences from the execution trace, and action sequences being just sets of actions that occur at a particular state. So we can have variable lengths of action sequences. So going through in this particular state, I'm going to see 1 action, then 2 actions, then 3 actions, and continue like that for a set of action length. And then based on the execution of those sequences, we using reinforcement learning options, we observe which of the sequences is best for the system. And here best means which of these sequences is helping us go to the actual goal of the system more than the other. And that is the reason why the system needs to have a defined goal, and the reason why we need to measure the progress of the system going towards that goal. And having that best sequence that we have there, then we can just generate the adaptation as we just saw, extracting the context as the state in which the sequence starts, and the behavior variation of the system as the individual actions that the system is executing in that sequence. So the way reinforcement learning options work is that first we need to define a reward for each of the actions in the system for a particular state. So this is just the basic definition of reinforcement learning, right? And again, that is the reason why we need to measure this way of progressing towards the goal. So intuitively, as in our example, as the robot gets closer to the delivery of the product, then we have a positive reward, and if the robot gets farther away from delivering the product, we have a negative reward. And doing this will help us manage the actions of the system. So the way options work in reinforcement learning is that we actually want to learn sequences of actions, not individual actions here. And there are many techniques to learn sequences of actions. One of those is using the cumulative reward of all the different actions in the sequence, and is the technique that we use here for Autocorp, as we want to take the sequence that is most appropriate for that particular state. So most appropriate here means we're going towards the goal state, and we're doing this optimally. So the robot is not going to walk around aimlessly in the warehouse in one of our particular sequences. And finally, having each of these sequences, we use the regular reinforcement learning process. So basically executing the sequence in the environment, observing the reward, and adjusting that reward for the state based on how good that is to reach the goal of the system. All of this process is broadly defined in this set of algorithms. So the first part is extracting that action sequences from the execution trace. So here for each of the sequences for a particular length of sequences, so 1, 2, 3, 4, 5 actions in the sequence, we extract the execution of the sequence and start accumulating that reward of how good was taking that action towards the goal of the system. Then we just use the regular reinforcement learning algorithm. So we're using plain Q learning to see which of the sequences has the best reward for. So for each of the for each execution of the sequence, we have the discounted reward over time of taking that sequence action on that particular state, and record all of those as possible options. What is going to happen at the end of the execution of this process is that we're going to have one option that is preferred over all other extracted sequences, and that is the options that we're going to extract for our system. And then we just need to enact that option as the adaptation we extracted for the system. So whenever we reach that particular state in which the action sequence takes place, what we do is activate the context we extracted from the environment and execute the option for that particular state. So for that particular context, and the option is going to be the sequence of actions with the best reward. And after that, we deactivate that context, reverting back to the base behavior of the system. And that's the way the general process in which reinforcement learning options work. And in the particular case of extracting adaptations for Autocorp. So does Autocorp work? Well, yes, it does. So to show you how Autocorp works, we're going to use the example of the warehouse robot. We have explored other examples used in other application domains. So for example, transport system management or driving assistance for autonomous cars, in which we have tried this, but in the interest of time, we are going to stick with the warehouse robot example. So in the definition of the warehouse robot example, you can see the robot working autonomously in this process of fetching a particular product and taking it to the delivery spot in the warehouse. And for each of the individual states, the robot needs to take a decision of what to do. And the what to do is one of these 6 actions available to the robot. And the robot needs to kind of learn for which state is the best action here. As we extract context, as we try to define special behavior for each of to describe this, the way in which the robot works, we need to take into account all the different products or the different states in which the robot can start here, right? So for each product and each state for the robot, we will have one of these contexts in which the robot needs to, the expected behavior of the robot is to go and fetch that particular product and then take it to the delivery place. So this can grow in the amount of states that you need to take into account, combining all the different states for the warehouse for all the different products. And then you need to do this for each product in the warehouse. So if you have to define this by hand, so the regular job of a developer working with context-oriented programming, you will have to find all of these contexts beforehand for your system. And doing this is time-consuming and is error-prone, so you can miss context or miss interactions between this context as the number of contexts grows quite fast, right? So using Autocorp, what is going to happen? The robot is going to learn which sequences of actions are best for each of the products for each of the starting states of the robot. So if we start here in the same initial state as the example before, the robot is going to learn that there is an action sequence that is going to take it closer to picking up the product and then dropping it off, which is the arrow here. So the decision points here are not each of the individual states of the warehouse, but just you can think about them as each of the arrows here. So the amount of decisions the system needs to take to be able to reach the goal is going to be decreased using Autocorp, and therefore increase automation of the system. So here we have 2 action sequences that are extracted. The action sequence to the right is extracted from whenever the robot reached the product and took it directly into the goal state, and this will happen as a single action on the system because it's executing that option here in the bottom right of the code, in which the robot is actually executing each of the 6 individual actions here, right? And this takes us to the end of this presentation about Autocorp. So the main takeaway message that you should receive of how Autocorp works and why it's important is that Autocorp is actually enabling context-oriented systems to take into account unknown situations in the environment and actually become adaptive dynamically to the environment. So if situations in the environment are changing, the system is able to see those changes and extract the best behavior variations for those particular changes that are happening in the environment without actually having to be predefined by developers. So Autocorp is actually is pushing forward the work in context-oriented programming. So to recapitulate the main points of Autocorp, we are actually we have a continuous execution process in which we extract action sequences for different special states in the system. These action sequences are the action sequences that are most appropriate to execute for that particular state. And from those, we generate the adaptations that are going to become context-oriented adaptations in the system. And to do this, we use reinforcement learning options that help us figure out exactly what the most appropriate behavior is, taking into account all the different sequences. Of course, this work is not done yet, and we still have to make some improvements in the execution of Autocorp. One of the directions that we're taking now is to explore more types of systems in which Autocorp can be applied. As I said before, we are exploring different application domains with autonomous driving, with system management, with this kind of like autonomous systems for the Internet of Things and Industry 5.0. And we are thinking of exploring different reinforcement learning techniques, for example, integrating lifelong learning techniques into our system to be able to manage the amount of adaptations that we are generating. Some adaptations may be discontinued, so we can kind of forget those adaptations and continuously include new adaptations following the interaction of the system with the environment. Thank you for your attention.